relates to some of the things we've heard this morning. For example, Rich talked about our policy methods, and see how we're able to do an analysis of the kind of methods that Rich was talking about, and hopefully improve on them to some extent. Also, we happen to be co-located with another meeting on the safety of dams. When people build dams, the population has the right to expect that the structures that are constructed are safe. It's an important topic. Similarly, when we design reinforcement learning algorithms, the consumer of these methods has also some right to expect that these methods have to be quote-unquote safe. So we'll see how we can try to guarantee safety of reinforcement learning algorithms under this same framework. And also we talked a lot about scalability, and we'll see how we get scalability.
Okay. Did you all hear me, or should I repeat what I just said? Oh, good. Okay. Now, one of the things you must learn if you come to the US is that the way you say yes is you shake your head this way. And this was something that took me a while to learn. Old habits die hard. Okay. So, anyway, the title that I picked was it's sort of a pun on the framework that uses this concept of mirror maps. I actually will not be sort of highlighting one particular algorithm as the best, because I don't think that makes a lot of sense. But I think the framework is quite useful in understanding a variety of issues in reinforcement learning. So if you're interested, there is a very, very, very long paper that explains some of these ideas. And I'm actually going to be talking a little bit about new results that we've obtained after we wrote this paper. I should also say the genesis of the paper, last year I had some issues with my health, and in particular, I received the sort of rather scary news that I could be going blind. And this was, as you can imagine, it's pretty terrifying. But fortunately, I had some really expert medical help. I'm in Massachusetts, and within driving distance of Harvard Medical School and the wonderful medical facilities in Boston. And so they were able to essentially do a miracle and save my eyes, and I can see all of you perfectly fine. But it also gave me impetus to finish this paper, and one of the things I did before my surgery was they pumped me full of steroids. I don't know if you've taken steroids, but it's one of these wonder drugs that allows you to work for 20 hours, and you're like, oh, I could work for 4 more hours, I don't need sleep. And so this paper was written in a space of 3 weeks, 15-hour days. But I don't recommend doing that. So it's kind of, you don't want to take steroids unless you have to. So I also want to say at the outset that this is really work that is due in large part to the effort of all the grad students that are listed on the paper. So really, a lot of the credit for the ideas go to these people. And it's based on about 6 or 7 conference papers, and there are more coming out as well. So we're going to propose a way of looking at reinforcement learning through the concept of what are called proximal operators. This is an idea that is well known in optimization, and we'll see what benefits it provides to its use here in reinforcement learning. In particular, we'll see that, as I mentioned, the use of proximal operators will allow us to design a framework for reinforcement learning that can guarantee, in some cases, safety. And we'll do this through a rather interesting approach of generalizing a class of methods that was studied in reinforcement learning by, in fact, a number of people in this room on so-called natural actor-critic methods, where you not only keep track of the value function like you do in, say, Q-learning, but you also keep track of the policy. In fact, the value function that is stored in an actor-critic is the value function that is associated with the policy that the agent is currently following. And this is a very rich class of methods that has had quite a bit of success, particularly in real applications like robotics, where you have continuous actions. We'll look at the problem of reliability. How do you design reinforcement learning algorithms, particularly TD methods that are guaranteed to converge? And I'm going to show you some new finite sample convergence guarantees for off-policy TD that I think are new in the literature. And finally, we want to look at scalability. How can we design methods that are truly scalable? So one way to understand some of the things I want to talk about is to return to the very basics of gradient descent. And here's a formulation of gradient descent that you might not have seen. So, so what is it saying? It's basically treating gradient descent as an optimization problem. So, we have the usual problem of some function f, which is differentiable, and we're trying to minimize this function. So we write this as the following problem. At every step, you're at some point where, let's say, your current guess for the minimum is at a point w sub k, and you solve the following optimization problem, which is find some vector u, which lies in the direction of the gradient of f at wk, and is not too far from wk. So in other words, move in the direction of the gradient, but don't go too far. And in fact, if you solve this, you get back gradient descent, which is perhaps a formulation you might not have seen before. This is going to be very important for us because of two core things. First, this is an example of a proximal construction, as we'll see. In fact, this is a proximal operator right here, and we'll see why that's important. Second, one of the key methods that I'll use, which is called mirror descent, is actually a generalization of this, where this term, which is in this case the second term that says don't go too far, is being measured here by Euclidean distance, and we'll generalize this to a more general concept of distance called Bregman divergence. And when we do that, we actually get out this idea called mirror descent. Rich?
Are you using a minus sign or something? You said you're trying to maximize closeness of u to the gradient.
Yes. So in fact, if you differentiate this, right? If you work through the math and differentiate it, you'll see it'll come out fine. So in other words, if you want to minimize this, right, you're going to take the gradient of this whole thing with respect to u and set it to 0. Solve for that. And the minus sign will appear. Trust me. Yes, Java.
Step size?
Ah, yes, okay, good point. I did not put a step size parameter here, and you can do that. You can put an alpha there, which would be your step size. Good point. Yes, I didn't do that. Okay, so remember this construction, right? Go in the direction of the gradient, don't go too far. And
Be the opposite of the gradient, and you take that first term really down. That would be.
well, so yeah.
When you said you want to make it close to the gradient, that equation seems to say you want it not.
So you're saying make this, which term now? You're controlling u.
That first term you described as making u close to the gradient, but it would actually...
Well, I'm saying this is the dot product, right? So you want to make this dot product as large as possible, or as small as possible, sorry.
Why do you want to make it small? That would make u different from the gradient.
Yeah, maybe I'm not describing it right, but this is basically saying how far away I am from the gradient, right? Because I'm taking the dot product.
And minimizing.
And minimizing, right, that's right. So going in the direction of, yes, you're right. You're right. So going in the direction of the negative gradient would make that term the way you want it. Yes. Java.
Yeah, can we view the first term,
Yeah.
this inner product,
Yes?
as essentially a linearization of the function at WK?
That's correct. So that's another way of looking at it. So if I add an extra term here, which is the value of the function at WK, just add that here, and that doesn't change anything because we're not minimizing with respect to it, right? Then this is just a linearization of the function around WK. So that's a good way of looking at it too. Thank you. Yeah, that's right. So just add f of WK right here, plus this term, which is just the Taylor series extrapolation. Okay, good. So scalability. Rich mentioned this morning that when we want something to scale, we certainly don't want to do things like inversion of matrices. But I'm going to sort of think about scalability in a stronger form than that. In other words, if you think of this as sort of some measure of the resources, it's an algorithm is taking time or space or whatever, and this is the problem dimension. We're going to hope for algorithms that are clearly not, super linear, whether they're exponential or high degree polynomial, but we want something that's not even linear. We want something that, in some sense, shrugs off the dimension. So you give it problems of larger and larger size, and the algorithm appears oblivious to the dimension. And that's going to be our standard. So why do we want something like this? Clearly it's desirable, but if you think sort of intuitively about human performance, by the time you've got to this stage, if you're an undergrad or a grad student here, you already know a huge amount. And as you grow older, you're going to learn and learn more and more. And it's not like, unless you get to a really old stage, you're not necessarily slowing down. It's not like the more you know, it takes somehow longer to access the knowledge you have. And so there's this almost dimension-free quality to our knowledge representation structures that we can retrieve information despite the fact that we know an enormous amount and we continue to learn more. So it seems like we should really be wanting something more than just linear. And so we're going to look at how we might be able to get something like that with this formulation. So one of the nice aspects of this formulation is that it really lends itself to a large number of different kinds of algorithms. I mentioned natural actor critic that we'll look at. We'll also look at off-policy gradient methods and see how we can analyze them. And finally, we'll look at sparse reinforcement learning methods. So the framework applies to a large number of different kinds of methods. Okay, so this is sort of my attempt to sell this a little bit at the beginning. Now comes the bad news. What is the bad news? Well, the bad news is that we have to go through some math. And I wish we didn't have to, but, well, you're all interested in machine learning, so you might as well get used to the fact that machine learning in 2015 is going to require you to learn a lot of math. I got interested in machine learning in 1981 when I wrote my first machine learning program, and it was a very, very different field then. Sometimes I wish for the good old days. Okay, so I don't really know how much convex analysis you know. I'm going to assume that you know very little. And I'm just going to sort of touch upon the basic concepts that we're going to need to understand the approach, right? So I'll walk through some of the main definitions. If it's all familiar to you, just you can sort of, read your email or do something else and eventually get back to paying attention. So there are three core concepts that we need to understand, and I'm going to walk through these with the background. So we need to understand this concept of what is called a mirror map. So what we're going to be doing is we're going to construct dual spaces. So we're all familiar with the primal space in which we do gradient descent, but we're going to construct this other space called the dual space. And we'll see why that's going to be important, and in particular the mapping from the primal to the dual space is going to be chosen carefully so that it allows us to design algorithms with some nice properties. I also mentioned the concept of proximal operators. This is the generalization of the concept of projection. we're all familiar with the concept of projection. So for example, if you're doing least squares, you're basically projecting onto, say, the column space of the design matrix or something like that. A proximal operator is a generalization of the concept of projection. So if you sort of write out a projection, proximal operator, and you look at a special case, you get back projection. But it shares a number of properties of projections, which makes proximal operators very, very convenient, and we'll see that they're extremely powerful tool in the design of machine learning algorithms. And I'll give you an example from a recent paper we did that's actually not in reinforcement learning, but it helps to understand this concept. And finally, we'll see later about how to formulate reinforcement learning using the concept of saddle point methods, which again give some advantages that we can exploit. Okay, so very, very basic. We're going to be looking at convex sets. These are sets that have particularly appealing properties. So the basic definition is if you take 2 points inside the set and join it by a line, all the points on the line are in the set. So that's convex and that's not convex. And there are many, many examples of things that we use in machine learning. They're all convex. So for example, hyperplanes, half-spaces, subspaces, polyhedra, and things that you might not think of as convex, but if you sort of work through the definition, you see they're convex. For example, the set of all positive definite matrices, the set of all non-negative matrices. Some of these form restricted forms of convex sets, such as cones, and we'll see that actually will be important tomorrow. And convex sets are closed under certain operations. For example, intersection of convex sets is convex, and things like that. So another reason convex sets are interesting is because the concept of projection. So if you project onto a convex set, you get a unique answer. So if I have this polyhedra here, and I have some vector x that lies outside it, I can find the closest element x star to x that lies within the polyhedron, on the boundary, obviously. And that's unique. Whereas if I went to a non-convex set, then there might not be one single closest element. And so we can just think of the projection operation this way, right? So if this is the convex set C, then x star is the projection of x onto the convex set C, which I can write as the simple quadratic optimization problem of finding the vector u in C that lies closest to x. So convex functions can be defined in a number of different ways. One way that is simple is to say that a function is convex if its epigraph defines a convex set. So what does that mean? So let's take this function here. What is the epigraph of a function? It's a set of all points that lie on the function or above it. Okay, so all the stuff that's here is in the epigraph. Now, a function is convex if and only if its epigraph is a convex set. So this is clearly a convex set right here, and similarly here, this is going to be a convex set, right? We can also more directly define convex functions as functions that have the following property, where if I take any 2 points and join it by a line, and I interpolate the value of the function on any point on that line, it lies above the actual value of the function at that interpolated point, which is this inequality. So if you've seen things like Jensen's inequality, this might be familiar. Convex functions are not always differentiable, and this is going to be important because we have to extend our notion of what differentiation means. But in the case they're differentiable, there's an important identity that we're going to use, namely that a convex function always grows as fast or faster than its gradient at any point. In particular, if it's a proper convex function, it grows faster than its gradient. And so here's a convex function. It's a strict convex function. That means it's strictly convex, so this is positive entropy. Now, if I take the difference between the value of the function at any point and the first order Taylor series interpolation of this function from some other point y, this difference is called the Bregman divergence. And this is a very, very important idea because it turns out most of the distance measures that we use in machine learning are special cases of Bregman divergence. This includes things like Euclidean distance, Mahadevan's distance, Kale divergence, and there are about a dozen or 24 distance measures, all of which are special cases of Bregman divergence, right? So the concept of Bregman divergence, and I'll define this more carefully later, is just a simple idea that I have here a strictly convex function. At any point, I do a Taylor series interpolation of this function, and at this other point, I look at the actual value of the function minus my interpolated value, and that's my Bregman divergence. Okay. So convex optimization is of huge importance in machine learning as well as in computer science. If you haven't done an optimization class, I highly recommend doing it because this is one of the things that you really need to know, and it's well worth the effort in understanding optimization. And it shows up in a number of different places in computer science. In particular, in our case, we're interested in things like agents and machine learning, and we'll see where it's useful. And in particular, in machine learning, a lot of the kind of criteria that we use to train our machine learning programs are based on minimizing some convex objective function. And in particular, they're not just a single objective function, but they're usually composite objective functions, right? So here's a classic example of sparse regression. So here I'm trying to fit some model, a linear model, but I want the model to be sparse if possible. So beta here are the model coefficients, y is the observed values, and x is my design matrix, which is the set of observations I make. So this first term is minimizing the mean squared error. And the second term basically is what sometimes called the L1 norm, the sum of the absolute values. And lambda is a regularization parameter that says how much importance I give to this, right? So if I make lambda to be basically infinity or very, very large, then the best answer is to simply set all the coefficients to 0, because that will minimize this term and you just completely ignore the fact that you're not even fitting the data. But by adjusting this, you can sort of minimize the fit to the data and, in some sense, the simplicity of the model. And this is called the lasso objective function in statistics, and it's been widely studied for the last 20-odd years. And in reinforcement learning, it turns out we can also formulate similar objective functions, and later we'll see this convex objective function actually that will turn into a minimax problem. We'll see why that's helpful. And in unsupervised learning, here's an interesting problem of constructing low-rank embeddings. And I'm going to walk through this example just to show you an example of how concepts of optimization are playing a role in machine learning. And this is an application that one of the projects that I'm involved in. And it's a fun project, so I'm going to say a little bit about it. So we're actually getting data from Mars. So many of you might know that there's a rover on Mars called Curiosity. It's wandering around Mars. It's going to be there for a very, very long time. It has plutonium batteries which last 20 years. You know, you might hear reports about where it's sort of going around and what it's doing. And it has lots of scientific instruments. One of this is a laser. So it can sort of be directed to zap an object, typically a rock. And then it gets back this sort of spectrum of readings from the plasma that's created by this high-powered laser. And it doesn't really have the compute power to analyze this on Mars, so this information is beamed down back to Earth, to the Jet Propulsion Lab at the California Institute of Technology, Caltech, and then it's downloaded to our lab servers. So we're sort of writing machine learning algorithms for analyzing what these emissions tell us. Now, one thing we can do is we have actually the very same instrument in the lab of my collaborator here, Darby Dyer. She's an astronomer on the scientific team of Curiosity. And so this is sort of a men in black picture of myself and two of my students. We're wearing these dark goggles because of the very high-powered laser. And so we're required to do that. So we can zap anything we want on Earth, typically rocks, and then we can compare the rocks that we zap on Earth to the readings we're getting from Mars, and we can say, well, you know, how do these things compare, right? So how do we formulate an optimization problem here? So I'm going to show you one particular approach that we just published in AAAI. And this is an area of machine learning which is basically doing dimensionality reduction. It's called manifold learning. So you might be familiar with some of the work in manifold learning. So there's some classic papers on this. But the basic idea is that the way we learn from high dimensional data, whether we're doing supervised learning or reinforcement learning, is somehow we hypothesize that the data has a low description complexity. One way it might have that is that if it lies on this sort of manifold structure. So this is a generalization of the simpler assumption that the data lies in a linear subspace, which is what typical linear methods like principal components analysis assume. So, and then we can try to empirically construct this manifold and then attempt to derive a lower dimensional structure by basically unraveling the manifold and computing a lower dimensional representation. But in this paper, what we actually do is we don't make this assumption, instead we make the assumption that the data lies on some unknown mixture of lower dimensional manifolds. Here represented as a dollar sign, right? There's two manifolds here, the S shape and the vertical bar is a dollar sign. And in general, we don't know how many such manifolds there are, and we don't know, in fact, anything about them, except that there's possibly more than one, and we have to somehow deal with this, right? So one way you can actually solve this problem is to solve one part of this involves an objective function like this. So let me just explain what this is. This is an example of a composite objective function. What is the first term? The first term, basically, X is your data set. And what it's saying is that, so when we say something is a manifold, for example, the surface of the Earth is a manifold, what does that mean? What it means is that if I stand at any point of the surface of the Earth, the world looks flat, locally. But of course, if I look far enough out, then I realize that the Earth is not flat. So similarly, if the data is lying on a manifold, it means that I can approximate it as a Euclidean space locally, not globally, right? So this tries to reconstruct every point as a linear combination of its neighbors. So you can imagine patches that go around every point and construct a local representation of this point. That's what this first term tries. The second term, and if you try to do this alone, it only works if your data lies on a single manifold. In fact, this will lead you to a method called locally linear embedding, or LLE. The second term basically says, in order to account for the fact that the data might lie on multiple manifolds, you need to make sure that you're not pulling out data points from another manifold if you're trying to reconstruct yourself. And one way to do that is to force the rank of the reconstruction matrix to be low. The rank turns out to be, unfortunately, a non-convex constraint, but it's often approximated by what's called the nuclear norm, which is the sum of the singular values, which turns out to be convex. So, so here's this composite objective function that we have to solve, Java.
Yeah. How is the locality expressed in the first term? Because you said that you're trying to locally reconstruct the points.
That's right. So basically, you know, R will turn out to be block diagonal, because we're essentially going to have a fixed dimension. Fixed
so there is
number
a
of
shape
years.
constraint on R,
That's
basically.
right. Yeah.
Okay.
Yeah.
Okay.
So, so here's a typical example of the kind of problem we want to solve, right? We have to minimize a convex function, which is the sum of two convex functions. One of these functions turns out to be differentiable, and the other one is not. Actually, this is the convex function that is not a smooth function. So we need a general solution to solve this problem. And we'll see that this has applications to reinforcement learning as well. Now, there's a lot of ways of writing optimization. There's a very general way of sort of viewing these as what are called monotone inclusion problems, which I won't get into too much. But we're going to go down this route of sort of finding what are called proximal mapping solutions to this sum of two convex functions, and then we'll see methods like mirror descent and how they help us solve these problems. So let's define a proximal mapping. So what is a proximal mapping? A proximal mapping is a generalization of the concept of projection. So if I have some convex function h, what is the prox function? So the prox function of any vector x with respect to h is simply the smallest vector u that minimizes the sum of h of u plus the second term, which is a distance term. So notice that the gradient descent thing that I told you about is very, very similar to looking to this, right? So find the vector u that minimizes the sum of the function at u plus it's as close to where you're evaluating the prox operator as possible. So that's the second term, okay? So we can plug in some examples. 0 is a convex function. If you make the 0, then the prox of x with respect to h is just x itself, so the identity mapping. But let's take the indicator function, right? What if h was the indicator function for some convex set C? Then what's going to happen is that this term is the indicator function, which means for all points inside the convex set is 0, all points outside the convex set is infinity. So my minimization will sort of be infinity for any point outside the set, so I'll automatically only consider points within the set. And then for points within the set, I'm minimizing the second term, which leads us to the concept of projection, right? So proximal mappings generalize projections in this way. Now, why is this useful? Because people have worked through a large catalog of these so-called proximal mappings for all kinds of functions. And you can just look this up, and if your problem falls in this class, you know how to solve it. So for example, I just showed you an optimization problem where I said I need to solve a problem that involves minimizing the nuclear norm. Well, it turns out somebody has worked out what the prox operator for that is, so I can just plug that in. So it helps it enormously in designing optimization methods, because if your problem happens to fall in a class for which there's a prox operator, then you can simply plug it in. And so I won't go through this list in detail. You don't have to really try to read it, but there's a very large number of these prox operators that are known, and you can look it up. This comes from a paper on proximal methods and signal processing. Let's look at one example, which is sparsity, right? So we said we wanted to minimize the absolute sum of the coefficients. Well, so it turns out that has a well-defined prox operator. So in this case, we're going to look at this function, which is the L1 norm of some weight vector W. This is a convex function. So, so here, this is going to be the L1 norm. And it turns out if you work through this, it's a very, very simple prox operator. It simply says that you take the weight vector, and for every coefficient, if its value is greater than or equal to lambda, you just take the difference of that with lambda. If it's less than lambda, it's 0, and otherwise it's the value of that component plus lambda. So what this means is that if you're trying to solve a composite minimization problem where you have one differentiable component, and the second component is the L1 norm, then it turns out the proximal gradient method that we'll just see is very simple. It says do the standard gradient and then do the prox operator, and you're done. So it very nicely systematizes the design of these optimization methods. Okay, now we also need to worry about the fact that convex functions are not necessarily differentiable. So how do we enlarge our concept of gradient, which if you've all taken calculus classes, you only learn about differentiable functions in a standard calculus class. So what if the function is not differentiable? So there's a concept of subgradient, which is a straightforward extension of the concept of a gradient, right? So if I have a convex function, then I can define the subgradient of the function in the following sense. So if the function is f, then what is the subgradient of the function at, say, some point x? It's the set of all vectors s, such that if I plug this in the Taylor series expansion of the function at x, I get a lower bound on its value at y, right? So remember that if I take a convex function and I do its Taylor series interpolation, I'm going to get a value that's lower than the value of the true value of the function. So any vector that's going to satisfy that is going to be a subgradient. Okay, so here's an example of some subgradients. And the set of all subgradients is what we call our subdifferential. So one important difference between a regular gradient and a subdifferential is that usually when you think of a derivative of a function, it's a unique value, unique vector, whereas the subdifferential is going to be a set. So let's look at a very simple example of the absolute value, or the L1 norm, if you want to think of it this way. So it's clear that for all positive values, it's just going to be the line, and similarly here, for all negative values, it's going to be the line with the slope -1, and at 0, it's 0. So the function is clearly differentiable here, it's differentiable here, and it's not differentiable at 0. So if a function is differentiable, then it's subdifferentiable. The subdifferential is just the gradient, right? So here the subdifferential is just -1, here the subdifferential is just +1, which is shown here. What happens here? Well, at the point 0, it turns out any value between -1 and 1 will satisfy the inequality we have, and so the subdifferential is the set of all points between -1 and 1. So it's an infinite set of points, right? So we have the subgradient method as the extension of the gradient method, where we take a function that's not necessarily differentiable, but it has a subgradient, and we simply walk in the direction of the negative subgradient, right? It's a straightforward extension of the standard gradient method, and we can do what is called the projected subgradient method. Namely, if we have some set of feasible values that we're considering, then at every step we walk in the direction of the negative subgradient, and we project back to our set of feasible solutions, and then we get the next solution, and we keep going back and forth. This is an extremely valuable method. It was designed originally by a Russian optimization researcher named Shor, who wrote a book on subgradient methods, and we'll see that it's the basis behind mirror descent as well. The only problem with subgradient methods is that they are extremely widely applicable, but they turn out to be slow. And so that's one motivation for trying to find faster methods. Now, since we have these set-valued mappings, right, the subdifferential is a set. There's some useful terminology that goes with that. So if I have a relation R, I can define something called the resolvent, which is defined as the identity plus lambda times the relation inverse. So how do we unpack that? Remember, a relation is simply a set of ordered pairs, right? X, Y belongs to the relation. So I can now define lambda R to be the set of tuples X, lambda Y. Now, I plus lambda R is simply the set of tuples X, X plus lambda Y. And I plus lambda R inverse is simply the flip for this, right? It's X plus lambda Y, X. And now we can actually reason with these relations, which is going to be important if you're dealing with subdifferentials, because if they show up in an equation, automatically summations will have to be turned into set unions, because now we're dealing with a set. In particular, what is the resolvent of the subdifferential? Let's see if anybody knows this. What is the resolvent of the subdifferential? You've already seen it. Hint. Okay? It's the proximal method. So let's see why. So if Z belongs to the resolvent of the subdifferential of some function f, right? So here's the subdifferential, right? Then if that's true, then it must be that x belongs to I plus lambda subdifferential of f at Z. And then you can just walk through the math from there, and you get this, which basically shows you that you've minimized the function at Z. So I should also mention that if I have a non-differentiable function f, so we know that if it's a differentiable function f, what is our condition for minimum? The gradient should be 0. If the function is non-differentiable but has a subgradient, what is the condition for minimum? The 0 should be in the subdifferential of the function at that point, right? So that's exactly this last condition here. Okay, so now we come to this concept of Bregman divergence that I mentioned. Why is it interesting? Because there's a large number of different things that it covers. And so, for example, relative entropy or KL divergence is a Bregman divergence. So let me define a Bregman divergence formally here. So if phi is some strictly convex function, then the Bregman divergence between x and y, and this is order is important, it's a divergence and not a distance because it's not necessarily symmetric, right? So the divergence from x to y is not the same as the divergence from y to x. Just like KL divergence from x to y is not the same as y to x. So the Bregman divergence from x to y is the value of the function phi at x minus the value of the function y, phi at y, minus this term, which is just the standard first order Taylor series distance between dot product of the distance between x minus y and the gradient of phi at y, okay, which is shown here visually. So if I plug in for the strictly convex function positive entropy and you work through the math, then you get back KL divergence. Okay. And Euclidean distance is also easy to see. Let me start with the strictly convex function to simply the norm of the vector. And if you work out what the Bregman divergence is simply Euclidean distance. Right? So you can similarly do this for lots and lots of different distance functions. Now, I mentioned composite loss functions. Well, there are lots of other places in machine learning where they show up. For example, in SVMs, we all know, if you've studied machine learning, you've probably taken a class where they covered SVMs. This is the standard hinge loss, where this term is differentiable, and this term, the hinge term is not differentiable. Similarly, here's sparse logistic regression, where the first term is differentiable, the second term is not. So you end up with these sort of soup of objective functions, some of which are differentiable and some of which are not. So we can sort of design a method that solves all of these in this way. This is called the proximal gradient method. So let's say I'm minimizing the sum of two functions f and g, where f is differentiable and g is not, right? So how do I design a method that can solve this problem? Well, I start with writing down the optimality conditions. If x star is the minimum I'm looking for, then I know 0 must correspond to the subdifferential of this function at x star, which is simply the gradient of the function f at x star, and it's a set union here, plus the subdifferential of the function g at x star. And then I go through a series of steps where, for example, I multiply by lambda, and I add and subtract x star, and I can work out, I end up with essentially getting back the proximal algorithm with respect to g. So g is our non-differentiable function. So what this does is basically do the standard gradient step on the part of the objective that is differentiable, and then do the proximal mapping on the part that is subdifferential, right? So this is now a very generic algorithm that you can now plug into, applications in machine learning. Okay, so we're kind of the last main idea that we need to cover, which is the concept of conjugate function. So in optimization, a very important notion in optimization is duality. And there are many different forms of duality. So for example, if you've done things like linear programming, you know about Lagrangian duality. I can write a linear program and then I can convert it to its dual by sort of computing Lagrangian. This is different. This is conjugate duality of a function. So if I take a function f, then this is the definition of a conjugate function, which is intuitively the largest distance between the function at any, say, vector x, and the linear function, which is simply the dot product of x and lambda. Okay, so lambda here is the new coordinate space over which we're defining the conjugate function. And you can show that the conjugate function is always convex, even if the original function is not. And in particular, if the original function I started with is differentiable, then this construction, which you can solve by just taking the gradient of this term, will lead you to the following result, namely the best value of lambda is going to be the gradient of the function at x, and this is nothing but what's called the Legendre transform. And this is going to be very useful for us. So here's the way of thinking about conjugate functions. So here's my original function, which is not convex. Here's lambda x, and I'm looking for the point where there's the largest gap between the linear function and the original function. And there are lots of interesting properties about conjugate functions, which you can find in a standard book on convex optimization like Boyd and van der Burgi. And there are other examples, I won't bother going through them. There's been one particular example we will use later, which is very useful. In particular, for example, relates to the stuff that the online learning work that Chaba was talking about, which is the p-norm function. So the p-norm function is simply the gradient of this following strongly convex function. I take a vector w, the length of the vector with respect to some arbitrary norm q, which might not be 2, it might be something else, right? It could be 1, it could be infinity, it could be some other number. So if I take the gradient of this with respect to w of the length, of the q norm length, then it turns out that I can design a Bregman divergence around that. And in particular, there is a dual function which is based on taking the p norm, where p and q are dual norms, namely 1 by p plus 1 by q equals 1. So for example, if p is 1, then q would be infinity. If p is 2, then q is 2, and so on and so forth. So these p norms turn out to be very, very important. And in particular, if you look at multiplicative algorithms in online learning, it turns out they can all be captured very nicely by an algorithm that uses these p-norm link functions for a large value of p. So this is the function that maps from the primal space to the dual space. So I start with my original weight vector w, and this is my mapping to the dual space, and then this is the mapping back to the primal space. So this is the original p-norm function and the inverse function, and we'll see how to use these later. Okay, so that was my very rapid whirlwind introduction to the basics of convex analysis. And now we're going to actually look at its use in reinforcement learning. Any questions before I continue? Yes?
So you define proximal mapping as means how you derive it. You take the of the differential part, you take the derivative, and then you take the proximal function, the non-differential part that you define. You take the
You mean proximal gradient or just the proximal definition? The proximal definition, there are no gradients, right? The proximal operator, it just says evaluate the function at some vector u and find the distance of that u from where you're evaluating the prox operator, namely x, and then find the vector u that minimizes that sum.
So you define how you find a minimum where a particular part is differentiable, but the other part is not differentiable. You just take the gradient of the differentiable part and then find the proximal mapping of the non-differentiable.
That's right. That's for the proximal gradient method.
So
yes.
is there a specific condition on the function g we are putting? So does it mean that we can minimize any function based on that? Like, or the f and g?
Well, we need to know what the prox operator is for that.
And means are there means.
And so, you know, if you either look it up in a standard table of prox operators or you derive it.
Or
you look at the
somehow
definition
it relates to the means functions category of some nice functions, convex functions, or something like that.
Yeah,
So,
I mean, there are some properties that have to be satisfied, obviously. Right. Okay, so our first example of the use of all these concepts will be safety in reinforcement learning, right? So I gave you this example of this rover on Mars, Curiosity, and it's like the perfect testbed for reinforcement learning, right? It's there for a very long time. There's nothing to disturb it. I mean, there's no other robots running around there. It can do a lot of exploration. Why doesn't NASA allow us to do that? Anybody? Why doesn't NASA say, great, Rich, would you like to try your latest off-policy TD algorithms on our rover on Mars? Well, one reason they don't, I mean, I can think of other reasons, but is that they're perhaps worried about safety, right? This is a $1 billion vehicle that was sent there, great cost, and they want to make sure whatever we do, we don't mess it up, so to speak. So they sort of trust the human operators that are running this thing. They don't trust the reinforcement learning methods. But we need to change that, right? We need to basically say, look, we can give you reinforcement learning methods that are just so reliable and so bulletproof that you'd rather use our methods than trust unreliable human operators. Right? It's a hard sell unless you can actually convince them that that is the case. And there are areas where that's actually happened, right? So for example, when we all fly, much of the standard flight that we take, I came through Frankfurt. It's a long flight from Frankfurt to Chennai. And a lot of that is completely automated. The flight is just flying. The pilots are just sitting by and watching, but it's on autopilot. So clearly we trust autopilot systems because they're reliable, they've been proven. So it's not like we can't solve this problem. We can. It's just that we have to sort of convince them that we have safe methods. And that's basically the challenge for us, right? So that's what we want to address. So I'm going to talk first about how we do this, and I'm going to use this method called mirror descent. And it unifies a large number of different methods, in particular gradient descent, but also things like natural gradient, which we'll see is going to be helpful for us. Some of the work that Chaba was talking about in online learning uses methods like exponential gradient, multiplicative methods. All of these turn out to be special cases of mirror descent. Lots of sparse learning methods by people like John Duchy. One interesting recent result that you might not be familiar with is that boosting, which is one of the most popular methods for training ensemble classifier, turns out also to be a special case of mirror descent, which is an interesting result. So mirror descent is very useful because it's sort of an umbrella method. So how does it work? So it's based on work that was originally done by two Russians. And there is a folk theorem in machine learning which says every great idea, except for temporal difference learning, goes back to two Russians, right? VC dimension, you have Vapnik and Chervonenkis. You have, mirror descent goes back to Nemirovsky and Yudin, and the list goes on and on and on. So these Russians, they had almost no computing in Russia back in the days when they're doing this, but somehow that helped them think very creatively. And maybe in order for us to replicate that, we should sort of maybe, Ravi should take away all your computers and you design better algorithms. Okay, so, and for a long time, they published this book. I don't know if you've read Russian books. The situation in India has changed a lot. When I was an undergrad and grad student, if you went to bookshops in Chennai, which I did a lot, and you bought books, chances are you got books by Russian authors, mere publishers in particular. And you get these massive tomes on calculus probability for like nothing. Cents, and beautifully printed and all that. Nemirovsky and Yudin sort of put out one of these books, and if you try to read the original book, it's completely impenetrable. Because nobody understood what the hell they were talking about. And it turns out there were two Israeli optimization researchers back in Tabo who digested the book and said, it's really this all they're talking about. And then everything was clear. So I'm going to show you, and this is a recent book by Sebastian Buback of Princeton that actually explains mirror descent in a nice way if you're interested. So what's the basic idea? So we are doing gradient descent in some space called primal space, right? And what we're going to do at every step, we're going to construct this Legendre transform, which is going to be a gradient of some strictly convex function phi. And that's going to map us to the dual space, right? So in the dual space, we're actually going to do the gradient. And once we finish with the gradient, we're going to walk back to the original space. And this time, we're going to use the gradient of the conjugate of the function we used here originally, okay? Because you can show that the gradient of the conjugate is nothing but the inverse of the gradient of the original function. So it's like an inverse mapping. So why would you do this sort of rather bizarre thing? Well, one reason is that if you think of the gradient rule, it's adding sort of the original vector x sub t to the gradient of the function at x sub t. And there's like a type clash there, because the smoothness properties of the space of gradients may be quite different from the smoothness properties of the original space. So this is something that mirror descent tries to fix by mapping these objects to the dual space, where presumably the smoothness properties would be better reconciled. But there are other reasons as well, as we'll see. So here's mirror descent, right? So this is one way to write the mirror descent rule for general, convex, perhaps non-differentiable functions, right? Which is, before I do the subgradient step, I'm going to map the original vector xk to the dual space using the gradient of some function psi. And then I do the gradient step, and then I map back using the gradient of the conjugate of the function, right? So here, gradient, back, okay? So what is mirror descent all about? Well, it turns out to be very simple. It's simply our original formulation of the gradient method, which I showed you at the beginning, where the second term, instead of Euclidean distance, I'm going to write as a Bregman divergence. If you just do this, it's done, right? Now, if Nemirovsky and Newton had said this in their book, okay, we'd all know mirror descent in the 80s, but they didn't. They sort of, well, you have to read the original book to see how difficult it is, but it was only written in the way the Russians can write. It's this sort of very thick style of writing. But it turns out that's all it is, right? It's just basically doing standard subgradient method, except when you measure how far you've gone, you use Bregman divergence. So in particular, if the Bregman divergence you use is Euclidean distance, then you get back standard subgradient or gradient methods. If you use other things that I'll show, you get back different things. In particular, we will use this because we're going to generalize natural actor critic using this construction. Okay, so here's an example from Beck and Tipple's paper. Let's take this entropy function, and let's use this as our Bregman divergence. And if you do this, this is the update rule you get, which is called entropic mirror descent. Okay, so here you're sort of gaining, this is an interesting construction. It actually, if you're familiar with the work on exponentiated gradient methods, it looks very much like an exponentiated gradient method of the kind that Chaba was showing in his presentation of online learning. Now, why is this interesting? It turns out, supposing I'm minimizing a function on the probability simplex, right? Then it turns out if I do entropic mirror descent rather than standard subgradient descent, then there's a huge savings in the sense that you can show that the worst case convergence guarantees, basically the dependence of the number of iterations will grow only logarithmically in the dimension of the problem as opposed to linearly in the dimension of the problem. So you get this huge savings by doing entropic mirror descent. There's also a nice recent paper by Nathan Srebro and colleagues, which appeared at NIPS, which shows that mirror descent is quote-unquote universal. What does that mean? If you take any online learning problem, for a very general class of online learning problems, including some of the ones that Chaba talked about, if a problem has low regret, in the sense it's a low regret solution, then it is learnable by mirror descent. So mirror descent is almost like a universally optimal method for solving this very broad class of online learning problems. Okay, now we come to the application to reinforcement. Yes?
So how does different functions give different minimas? So what does the give two different, let's say I use phi 1 and phi 2, and it gives two different minimas.
You mean use two different Bregman divergences?
Yeah, two different functions. So you get two different minimas. So what do you say about, how do you characterize these two minimas?
So that's a good question. So essentially what will happen is if you, so if you look at the convergence proofs for mirror descent, then they will sort of be dependent. So for example, if I take entropic mirror descent, and you look at the convergence proof of entropic mirror descent in this paper, it will depend very critically on the properties of the particular function you picked. So if you pick something else, then this, for example, minimizing the function of the property simplex, you're not going to get the same result necessarily. So there's some intelligence that's there in order to pick this function. So if you think about what's happening intuitively, right, at every step of gradient descent, you're walking along and you're taking steps, right? So by choosing this function, you're sort of controlling the size of the step that you take. And so by choosing different size, you're going to get, different convergence results. And that's going to depend in some sense on the geometry of the space. This is actually what Nemirovsky and Newton tried to explain in the original book, but it was all written in the language of Hilbert spaces and in a very, very general way, using functional analysis. It made it very hard to understand. And when you unpack it in this way, it makes it easier. Although you probably think maybe it's still hard, but it's a lot easier than the original book. Yes?
Yeah, so especially in this probability simplex case, where let us say sigma xi is equal to 1.
Right.
Right, so now I have a chance that I will go outside of space, then that's why I'm trying to project it.
Right.
Suppose I reparameterize the problem saying xi is equal to e power yi divided by sigma of e power yi.
Yeah.
Now the yi's are unconstrained in a way. So is it just that after everything it's somehow mapping to some kind of reparameterization, or does it go deeper than that?
Well,
Because
I mean, you can view it as a reparameterization.
So that's the most natural reparameterization you would.
That's
simple
right.
trick that by observation you would do, right?
That's right. So you can think of it, if you want, as a reparameterization. I mean, it's hard to explain without actually walking through the proof of convergence. And you'll see exactly how the bounds show up in the proof and how the result, they depend on the properties of this. So for example, here, I'd have to know exactly some properties of this entropy function, So if I start, for example, at the point where all the values are, say, half or something like that, or 1 by n for probability simplex of dimension n, then I have to know what is the largest, I have to know the diameter of the space measured by this function, right? So that term will show up, the diameter of the space. That's going to depend on the particular strictly convex function you pick. Okay, so now it's well known that for a long time, and in fact the first person to show this, actually first let me state the result, which is if I take the set of all probability distributions, so let's take a simple example, let's take one-dimensional Gaussians, right? So we know a one-dimensional Gaussian has two parameters, the mean and the variance. So I can think of that as simple Euclidean space, right? So for example, I can think of the x-axis as being the mean, positive or negative, and sort of the top half of the plane being the variance, because the variance is always non-negative or positive in general. I can think of it intuitively as maybe the half plane. But it turns out this is a very wrong way to think of the space of all Gaussians. In fact, it has hyperbolic geometry. The space of all Gaussians is not Euclidean. Similarly, the space of all probability distributions is a curved space. And you can actually measure the curvature of the space using something called the Fisher information matrix. So who was the first person to point this out? It's a very famous statistician who happened to be Indian. Rao, right? So this, if you do statistics, you run the lots of theorems with the word Rao, so Rao-Blackwell theorem and Kramer-Rao theorem and so on and so forth. This is some of the things, the result that he proved in his early 20s, and it's a very classic result. So Amari is a Japanese researcher who's been sort of studying neural nets for a long time, and he argued that if neural nets can be thought of as encoding probability distributions, then you should really be using natural gradients instead of Euclidean gradients in neural nets. And he did a lot of work trying to publicize this concept of natural gradient. So in a natural gradient, what you do is you do the standard gradient step, except you pre-multiply your gradient by the inverse of the Fisher information matrix. And what that does is it sort of warps the dimensions of the problem so that it corrects for the geometry. Okay? And what we're going to show is that this is actually just a special case of mirror descent. And it's very surprising that this result, as far as we know, has not been published before our NIPS paper in 2013. But if you find a reference where mirror descent is shown to model natural gradient, I'd be very interested in that. Okay, so I don't know if you can read that, but I'm going to walk you through the core proof. It's because it builds on everything we did, right? So here's the theorem from our NIPS paper. It basically says the natural gradient descent update at step k with some metric tensor at gk. So we pick some arbitrary metric tensor at gk, but you can think of this as, for example, inverse of the Fisher information matrix or something else that captures the geometry of the space. So here is the natural gradient step, right? Which is you're at some point xk, you walk in the direction of the negative gradient of the function you're minimizing, modulated by the inverse of this matrix, which is, in some sense, you think of this as a Newton step, because in the Newton step, remember that you're dividing by this second order Hessian term. So similarly, we have the second order inverse of this tensor. Okay, so that gives us this thing. We want to claim that this is just mirror descent with a very specific Legendre transform defined by the strictly convex function half x transpose gkx. So namely the quadratic form, the norm of x measured with respect to the tensor g. Okay, so how do we prove that? First, we just take the gradient of psi as defined here, and that's just nothing but gk times x. Okay, it's easy. Now let's define the conjugate function with respect to this. So here's our function, original function. Now we're going to compute its conjugate. Okay, and we plug in the definition. It's simply the max over all vectors in our primal space of this linear function x transpose y minus the original function. Okay. Now this is a strictly concave function, so that means it has a unique max. So we find its max, that's the unique max. So we can, and it's differentiable, so we can take just the gradient of this. And if we solve that, we simply get x equals gk inverse times y. We plug this back in here, and we can sort of do some more manipulations. And we plug it into, now we know the form of psi, the gradient of psi, which we got from here. We can also compute the gradient of the conjugate of psi, because we know the conjugate of psi, which is here, so we can compute its gradient. And since we have the gradient of psi and the gradient of the conjugate of psi, we can plug that into mirror descent. And if we do that, we get this. Okay, so this is mirror descent, where all I've done is, this is the gradient of psi from here, and then the gradient of the conjugate of psi, and then I manipulate this and I get back natural gradient. Okay, so this shows that the natural gradient step that is just a special case of mirror descent with a particular strictly convex function. Okay, so now we can take this and now we can plug this into an actor-critic method. Okay. Now, how many people here are familiar with actor-critic methods? I was afraid of that. So, I actually didn't make slides, but I did the next best thing, which is yes.
So the previous slide, you're basically saying that the standard second order scheme where you use the Hessian inverse, right? So
Yes.
That's basically mirror descent, right?
Yes.
But so how could you leverage this to basically do second order methods in a different or a better way? Sort of, because we know if the Hessian is big to invert, then there are some approximate ways of doing this, right? So
Yes.
how would you
yes.
leverage this viewpoint to try and sort of improve this, if at all?
Well, in some sense, that's what we're trying to do here, right? So we're trying to sort of say, you know, if natural gradient involves inverting with this Hessian, can we somehow use mirror descent to do this more effectively? That's basically, in some sense, if you think of what we're trying to do here. Okay, so This is actually an actor critic paper that was written by several people in this room, in fact. So the way actor critic algorithms work is that you store the value function of a specific policy that the agent is following. And so think of the agent as comprised of an actor who's following a policy and a critic who's evaluating this policy by constructing this value function. And there is sort of this interesting dance that goes on between the actor and the critic in order to learn the optimal policy. It's a very interesting class of methods, and in fact, the methods were actually developed a long time ago, almost 30 years ago or more, but the analysis took a lot longer than that, and in fact, it was people like Borkar and Shalab and others who laid the groundwork for the analysis of actor-critic methods with two-time scale stochastic approximation theory. So here's the classic actor-critic architecture where we have, we start out with some random initial policy, which is parameterized by some vector theta. We have some value function expressed as a set of feature vectors, and we start with some initialization of this policy. And then we do the standard reinforcement learning loop where we take a step, we draw an action by sampling from our policy. We observe the next state in accordance with the dynamics of our Markov decision process, and we get our sample reward. Now we do our update, and the update is going to comprise of two parts. One is, of course, we compute the TD error in the normal way, and then we do the critic update and the actor update, and these will depend on the specific kind of actor-critic algorithm you use. This paper goes through several different ones, and I'll just go through one of these that, I won't do the regular gradient one. I'll do the one that involves constructing this metric tensor. So what we do is we take the gradient of our feature vector at every point, and we incrementally compute. We take the order products of these gradients, and we form this matrix, right? G, and then we can basically do the natural gradient step with respect to G. So, for example, here's an example of doing that where we actually take the inverse of G, like I showed you before. Okay. So we're going to design a safe natural actor critic by basically mapping this to a mirror descent, and then taking advantage of the fact that mirror descent has the ability to make sure projections, we can always project back updates to some safe region, right? So that's essentially what we're going to do. So the application that we did in this NIPS paper was, we did two kinds of applications. One was this interesting robotics problem. This is a robot platform at UMass developed by in Rod Gruppen's laboratory called a U-bot, which is sort of has this inverse pendulum dynamics. It's this wheeled robot with hands, and it has this simulator that we used. It's a pretty high-dimensional robot, and what we showed in training this system was that the PNAC method learns a policy that essentially prevented this robot from falling down or getting into some dangerous regions of the control space, and the variance, in fact, was far, far lower than the standard natural actor critic method. So this is one application of this. Now, in order to do this, there was this lengthy sort of derivation of the safe projection step, which I will not get through, but it's in this paper. And in fact, we have a newer paper that, if you're interested, so if you're interested, send me email and I can send you this paper that we've written that sort of extends the results of our NIPS paper. And in particular, one of the key things in this is that, so I mentioned this classic result that the set of all probability distributions forms a manifold, and so you can measure distances in it with this tensor. And it turns out that all previous work has assumed that this tensor was positive definite. This gets back to the discussion that we were having earlier today when Rich was talking on the distinction between positive definite and positive semi-definite. And it turns out it's not true that the tensor is always positive definite. In fact, it's only positive semi-definite, and that has an impact on natural gradient methods that were overlooked. And Phil Thomas had an ICML paper last year showing convergence of natural gradient methods under this more relaxed condition. And so we've incorporated that in this paper, and there's some additional theoretical results as well. Okay. So that's safety. Now I'm going to get to the next part, and I suspect that's probably the only thing I'll have time for, which is reliability. So we want reinforcement, yes?
You mentioned that you set up a metric tensor for the Riemann manifold. So when you showed the connection between mirror descent and natural gradient, can you think of G inverse grad f as the mapping from the Euclidean space to the Riemann manifold?
So you mean this product?
Yeah. Can you think of that as a mapping from the Euclidean space to the Riemann manifold?
Yeah. I mean, that's one way to think about what it's doing. It's basically rewarping the space so that it's correcting for the fact that not all dimensions are sort of, I mean, the dimensions are not necessarily orthogonal in some sense. So it's sort of correcting for that. Yeah. Okay. So how do we design a reinforcement learning method that is reliable? In particular, we're going to focus on off-policy TD learning, and Rich already set the stage for that this morning. So makes it easy for me. So I'm going to sort of talk about some recent work that I've done with two students, Bo Liu, one of my current students, and Mohammed Gawamzadeh, one of my former students who's now at Adobe Research. So first thing is, why do we need a new formulation? Well, it turns out that the previous attempts at doing gradient TD are not quote-unquote true gradient methods, right? And I'll just sort of point you to Chaba's book for that, which asserts that fact. And also, if you look at the papers on gradient TD, the proofs have relied on stochastic approximation theory, haven't given us things like finite sample analysis and things like that. So, so we had this discussion before on the first day when we said, well, the TD algorithm, there isn't a function that we can write saying, if I take the gradient of that function, I get back the TD algorithm. We can ask that same question here, which is, well, we have these gradient TD methods. Is there a way of writing down some objective function such that the gradient of that objective function will give us these gradient TD methods? Okay, so that's our first question. And if the answer to that is yes, then in some sense, what does that tell us? Does that tell us any way of improving these methods? As we'll see, the answer to both is yes. There is a way of writing down an objective function, but it's not the original objective function. It's a different one, right? So let's go over what this original objective function was. So this is, one of them is called the mean square projected Bellman error. So remember, here's how it goes, right? We start out in some area of, we sort of have the value function represented with respect to some features, which are columns of this matrix phi, and theta is the linear combination of these columns, and that gives us our value function. We do the Bellman backup. That gets us perhaps out of our space that we can represent. We project back into the space, and we keep continuing on this, right? So we can measure the error between the place where we start and the place where we end up after we do the projection. And this is the mean square projected Bellman error, as opposed to the mean square Bellman error, which is simply the length of this vector here. So we can sort of view the problem as minimizing this term. And this is just the length, so it's a differentiable function. Let's just write its gradient and minimize it. How hard could that be? Where do we get into trouble? 0 for all. Why do you say that? The minimum. Yes. But we're going to take the gradient of this function, right? So let's just walk through this derivation so that we see where the problem is, right? So once again, I'm going to appeal to the paper. Okay, so there was this very, very nice paper written by Rich and Chaba and Shalab and a bunch of other people, which appeared in ICML 2009 on gradient TD. If you haven't read this paper, I highly recommend it. It's a very nice, nicely written paper. Okay, so let's walk through what happens here in this core step. And here it is, right? So this is the projected Bellman error. So this is our value function, which lies in our space, v theta, minus the projection of the backed up value function, right? With respect to some norm that is defined by the probability of sampling, visiting a particular state, right? So we expand this out. This is just a norm, so we can, and in fact, we can pull out the projection operator because v theta is already in our space, so the projection of v theta is nothing but v theta. We pull that out. We expand this norm to be just this. This is the norm with respect to the matrix D, the diagonal matrix D. And we walk through this, and what happens? We get here. And now we're in trouble. Because now we have a product of expectations, right? And so we can't sample easily from this. So what was done in the original paper was you basically you break this up into two parts and you design the method around that. And that's fine. And it was shown that this does converge in the limit using stochastic approximation theory. But it means that this is not a true gradient method because you did this sort of breaking apart thing. So can we sort of fix this part so that in some sense we retain the fact that it's a true gradient method? This is what I want to show you how we can do. So to do this, first what I'm going to do is, actually there were two methods, two measures. I talked about mean squared projected Bellman error, but there's another one called the sort of gradient of the expected TD update, NEU. Turns out both of these can be written in one form. There's some auxiliary matrices that are useful, for example, the covariance of the features, and some of these were already previously talked about. So we can, to make a long story short, we can write both of these objective functions in this one way, where if I choose for the matrix M identity, I get back NEU. If I choose the covariance matrix C, I get back mean squared projected Bellman error. So we're just going to work with this one generic form. So, well, we already saw this. This is showing that the same problem happens when you take the gradient of NEU. So we have these methods. It's just that they're not gradients. They're not derived by gradient of the original expression. So we're going to try to do something interesting here. We're going to say, well, clearly, it's sort of, when I remember hearing a math lecture once where the guy said, well, you see all these math papers written, and sometimes you wonder, why would someone think of such a bizarre problem? And it turns out a lot of the math papers are written, the way they're written is that people start with an original problem, and they find they can't solve it. But along the way, they manage to solve something else. And then they say, oh, that was the original problem we were trying to solve all along. And they write the paper up that way. Just one explanation for why some math papers look strange. Why did someone think of this particular problem? So we're going to do something like this. We're going to say, well, clearly the original objective functions are not what we want. But can we think of some different objective function whose gradient will give us this? Then we're in good shape because now we can start doing something, okay? And to do that, I'm going to introduce this saddle point formulation. So we're going to talk about saddle point problems. So in case you don't remember what a saddle point is, a saddle point function looks like this. It's not a convex function. It's a function that is convex in one dimension, namely this dimension, and it's concave in the other dimension. And saddle point functions are hugely important in optimization because they show up all over the place, right? So here's one formulation of a saddle point function that turns out to be important. A number of people have studied this. And so we're going to start with this. So this is the saddle point with respect to two parameters, theta and y. For example, f is some convex function, k is some smooth function which satisfies some conditions. We're going to start with this, and it turns out we can define an error function of the optimal solution to the saddle point problem with respect to any point where we are. Supposing we are at some point theta prime, y prime, we can look at the maximum. So remember, in one case it's concave, so we can do a maximum there. In another case it's convex, so we do a minimum there. So we take the difference between those two, and that gives us our error function. Okay, so we're going to choose a particular form of this general saddle point function where we take the f function to be 0 and the k function to be the norm, the squared norm of the vector y with respect to m, where m was that matrix that we chose cleverly to be identity or the covariance matrix of our features. Okay, and it turns out that this value can be shown to satisfy the conditions that we had. And so with this we can prove the main result. What is our main result? That GTD and GTD2 are true stochastic gradient algorithms with respect to this objective function, the saddle point objective function, where we choose m is equal to I or C respectively. And the proof is not very difficult. Okay? So now, what we've shown is that indeed these are true gradient methods. They're just not true gradient with respect to mean square predicted Bellman error, where we thought it's a little different. So, okay, but what does that give us, right? So one thing we can do is to say, once we have that, we can start doing all kinds of analysis. And since I'm almost out of time, I don't have time to go through the analysis, but we can prove some interesting theorems. And here's an example of a kind of theorem we can prove, which basically tells us that if you run, say, GTD for n iterations, then with high probability we can bound the error of the algorithm with respect to the parameters that we have. For example, the discount rate and other parameters, the reward function, and so on and so forth. This is an example of the kind of result we can show. Now, because now we have a true stochastic gradient algorithm, and we can tap into all that we know about finite sample analysis, and we can show these kind of results. We can also show performance bounds results for off-policy learning, building on previous work by Zico, Coulter, and others, where we can give error bounds on of the kind that people do when you do value function approximation. So the last thing I want to say is, okay, so we can all do all of this, but can we do more? And by more, I mean, can we design sort of better off-policy TD methods? And the answer to that is yes. And for that, we're going to need one key idea, and I'm going to talk a lot more about this idea tomorrow, but I'm just going to show you what it is. And this is the concept of the extra gradient method. Now we come to another Russian, Korpolovich, who developed this method, and it's a really clever, very ingenious method. It was developed for solving saddle point problems and as well as solving variational inequalities, which we'll see tomorrow. So what is the extra gradient method? So remember, in a standard gradient, you start somewhere, you walk in the direction of the negative gradient, and if you're doing projected gradient methods, you project onto the space and you're done. In extra gradient, you do two steps. So here I'm illustrating this for some arbitrary vector field f, but think of this capital F as simply the gradient of some function, small f, right? So I start at some point xk in the feasible space k, walk in the direction of the negative gradient, project back. And normally I'd be done at that point. What extra gradient does, it says, no, now walk again in the direction of the negative gradient, except at yk, then go back and pretend that that was the direction that you should have walked at in the original point xk, and make that adjustment correspondingly, okay? So do one gradient step, do the adjustment, and then recompute. So this is an illustration of the extra gradient method for minimizing some, function f. Okay? Now, well, one trick to writing papers is that every algorithm you can see that's out there, you can quote unquote mirror descentify, right? This is how people write papers, which is you have a hammer. If you have a hammer, then what? Have you heard the saying? If you have a hammer, every problem looks like a nail, right? So I know mirror descent, I see extra gradient, what do? I ask myself, is there a mirror descent version of extra gradient? And that's exactly what was done. It's called mirror prox. And this was done by Nemirovsky, who's now at Georgia Tech, by the way. And so this is how extra gradient works for mirror prox. You map to the dual space, but now you do the extra gradient step in the dual space, right? Which is 2 gradient steps. And then you map back to the original space. There are reasons why you can do this, and I won't get into that. But we can apply this back now that we know that these are true gradient methods. We can fit them into this proximal family, and we get accelerated versions of our gradient TD methods. We call this GTD-MP for mirror prox and TDC-MP. And we can study these and compare them theoretically and experimentally to the original methods. And the various results we have, they show that these newer methods have better convergence, lower variance, and I think I showed this yesterday. Here's a problem that we studied recently of sort of battery energy savings, so sustainability kind of domain, where we showed improved performance of these newer methods with respect to the performance of this particular task. But this is clearly a place where a lot more work will be done by my students and hopefully others as well. We seek to understand the space of true gradient TD methods better. I'm out of time, so I don't have time to talk about scalability, but we can tap into the properties of mirror descent to try to design reinforcement learning algorithms that in some sense have this property of being kind of oblivious to the dimension of the state space and so on. So I hope it gave you a little bit of the flavor of this framework that we've been developing and its sort of broad appeal and application across the landscape of reinforcement learning. And I welcome you to read this mammoth tome that we wrote, and in due course we'll be revising that and submitting it for publication somewhere. Thank you. Right. Yes. Yes, so you have to have 2 projection steps, which is considered one of the weaknesses of extra gradient, is that if the projection step is expensive, then you have to do 2 projection steps. And there's been a lot of work on sort of trying to make extra gradient methods faster, and people have tried to see if you can get away with just 1 projection step. There's a lot of work on that, yeah.